Hello and welcome to this new video presentation series on an example strategy for delivering and managing change in complex organizational environments. The approach we will take is to use digital twins, so we will review what a digital twin is, why you would want to use digital twins, and some of the ways in which you might build digital twins as part of a digital twin platform. But before we get into the world of digital twins, let's quickly recap on the world-class thinking framework that we covered previously. Please note that you don't have to have reviewed and studied the world-class thinking framework to build digital twins, but it really helps. It helps because using the framework will enable you to target in on exactly what you need to change in the organization and how to make that change successfully. With this blueprint in your hand, you can extract the relevant parts and codify them into the digital twin. As you will come to discover, this is a very powerful approach. This is because transformational change no longer needs to be documented in static, soon-to-get-out-of-date Word documents or PowerPoint presentations. Instead, a real-time source of truth is created, which captures the essence of the transformation for the system in question, as well as being able to track and manage any ongoing ancillary changes to that system.
In case you have not gone through this material previously, we will quickly provide a recap on the three foundational pillars of our world-class thinking framework. Once we have gone through the recap, we will then move on to the focus of this presentation series, digital twins. The first pillar, as you may recall, is Getting Things Done, or GTD for short. GTD is a personal productivity system developed by David Allen, who published a book of the same name. The GTD method rests on the idea of moving all items of interest, relevant information, issues, tasks, and projects out of one's mind by recording them externally in a trusted systems of record and then breaking them into actionable work items with known time limits. This allows one's attention to focus on taking action on each task listed in an external record instead of recalling them intuitively. Why is this so important? Because in the context of work, particularly in larger organizations, many transformation programs fail before they even start. They fail because many people don't have the necessary mental capacity due to the stress and anxiety that entails from keeping a vast amount of real-time activity and actions in one's mind whilst on the go. Put simply, our minds are not designed to be organic personal organizers. When working with very little natural mental capacity available, this makes it difficult to onboard new ways of thinking, to create new habits, and to learn new skills. As we said previously, if you are feeling stressed, burnt out, anxious from work, then stop what you are doing now. Get GTD, read it, and act upon it. Taking the mental to-dos out of your mind and putting them into a system of record that you have created and personalized for you is one of the most simple and powerful things you can do for your mental health. Trust me, you will be glad that you took the time to do this. The second pillar is based upon developing a strong systems thinking mindset, along with the ability to solve complex problems by having a comprehensive set of logical thinking tools and processes. This plays a big role in helping us to identify the root causes of problems and then to formulate the appropriate solutions that will stand the test of time. We live in a world of systems. In fact, everything in the world and everything in the universe is part of some type of system. Having a system-thinking mindset makes a huge difference in terms of looking at the bigger picture, and when combined with logical thinking tools, we are able to truly understand the systems around us. We are able to determine what's really wrong with those systems and then put into place the necessary corrective actions to change those systems. Currently, we are very much living in the age of the ego, in which many people shoot from the hip a vast range of views, perspectives, ideologies, visions, options, etc., without much forethought or insight. Secondly, very often we take on a technology-first approach. When we come to discover a pain point, we quickly formulate a technology solution, hoping that it will provide some form of quick pain relief. More often than not, this does not help and only makes the world around us much more complex, intense, and in some cases more dangerous than it needs to be. Shooting from the hip almost never provide communications of real value and simply adds to the global noise. In the case of technology deployment, deploying technology too quickly or deploying the wrong technology simply accrues more technical debt and very often at great expense. The focus of our training around Pillar 2 is the theory of constraints, or TOC, created by the Israeli physicist Eli Goldratt. TOC provides a very powerful foundational platform, along with logical thinking tools that will give you a powerful set of skills that you can use for the rest of your life at both a business and also at a personal level. The bulk of our training material will be around Pillar 2, and we should point out that, although it's not difficult to learn, there is a lot to learn, and it does require commitment. It also requires you to do a lot of thinking, so it does take some effort. In addition, we also incorporate some elements of lean, such as value streams, but this is more focused on complex enterprise organizations rather than specifically lean manufacturing. The third pillar is based upon Time to Think by Nancy Kline. As part of the creating this framework, Nancy identified 10 behaviors that form a system called a thinking environment. The thinking environment is a model of human interaction that dramatically improves the way people think, and thus the way they work and live. Listening, the quality of people's attention for each other, is the core of this method. Using a process of asking insightful questions, limiting assumptions start to dissolve, which is the key to unlocking deep insights and wisdom from within people that can then be used to help solve really challenging problems. Time to Think is extremely powerful because the thinking environment that it helps to create gives us a peek into our true nature, in which a vast treasure trove of knowledge and wisdom is revealed, which then becomes available to the thinker. Time to Think is a perfect complement to TOC, and in many cases supercharges TOC because of the incredible wisdom that can be brought into the logical thinking processes. For example, Time to Think is really useful in situations in which there are opposing opinions around how a system should be transformed that are being underpinned by either limiting or incorrect assumptions. Time to Think is really easy to learn, and in many ways it can be likened to a spiritual experience, but it's very different from the traditional communication patterns that you would find in a typical corporate environment. For Time to Think to be successful in an organizational setting, this requires that the organization is progressive in its way of thinking and enables safe spaces for people to reveal their best thinking. The last point of discussion from this slide is around digital twins. In the context of an organization using the 3 pillars to unlock world-class thinking in people, this will provide a large range of foundational layers that can be used to drive all sorts of transformation processes. As part of this process, a lot of knowledge that was previously locked in people's minds now becomes publicly available. What we don't want to do is have this knowledge trapped in static systems that begins to age and get out of date very quickly. What we do want to do is to capture this knowledge and to model it using a digital representation of that knowledge for a given system that we call a digital twin. The technology exists today to take these sets of knowledge and to model them as digital twins and to keep these digital twins up to date in real time. When we do this, it opens up a vast range of transformational opportunities because systems are no longer floating around in the ether as abstract constructs. Instead, they are now tangible systems that we can interface and interact with. On our experience, most business transformations are often less than successful for a number of reasons. 1. For organization-wide transformation to be successful, everybody needs to get on the transformation bus, and everybody needs to bring their A game using the best possible thinking available. Hopefully, the 3 pillars of our world-class thinking framework can successfully provide this. 2. The transformation is relying on inaccurate data. 3. The data is accurate, but it's been interpreted incorrectly. In theory, digital twins should enable us to work with highly accurate data, and secondly, to ensure that this data is being interpreted correctly. So, as part of this presentation, we will have a dedicated section on high-level architectures around how to create digital twins to support true business transformation. Don't worry, it won't be super technical. We'll try keep it high-level enough that it's suitable enough for a broader audience, but relevant enough to make it of value. To conclude, if we can unlock world-class thinking in all people within the organization using the 3 pillars, and then capture that knowledge through the mechanism of digital twins, we are then in a much better position to take the organization forward. This can provide a significant role in helping to deal with what will be challenging times ahead for all of us in the new global economy, the new global workplace, and of course, in the age of AI.
So now that we have laid down a starting point, let's discuss what a digital twin actually is. A digital twin is a dynamic, real-time, virtual replica of a physical object, system, or process. It uses data from sensors in the real-world counterpart to create a living model that evolves over time, enabling businesses to simulate performance, monitor operations, predict failures, and optimize decisions without physically interacting with the original asset. Digital twins can be used for a wide variety of use cases. In an enterprise context, digital twins are being used to create real-time, dynamic models of complex systems, spanning technology, operations, people, and customers. Within IT and cloud infrastructure, twins can simulate data centers, cloud deployments, and security architectures, enabling organizations to test resilience, optimize performance, and validate compliance before making production changes. In cybersecurity, they provide a safe way to model firewall rules, identity policies, and threat scenarios, allowing teams to identify vulnerabilities, rehearse responses, and demonstrate regulatory alignment without impacting live systems. Beyond technology, digital twins are increasingly applied to core business operations and strategy, which is our use case. Supply chain and process twins allow leaders to stress test disruptions, uncover waste, and improve throughput. Workforce and skills twins model organizational design and talent capacity, while customer and product twins simulate how people interact with services, products, or pricing changes. At the strategic level, enterprise risk or M&A integration twins give executives a forward-looking lens to evaluate decisions under different scenarios. Together, these applications position digital twins as powerful tools for enterprise governance, bridging real-time operational awareness with predictive decision-making. When executing any type of transformational change, if possible, the strategy should be, in our opinion, to create a digital twin of the system that is being transformed. By creating a digital twin, you are creating a real-time system of record that accurately models the system in question and helps to keep that model up to date in real time. This opens up a huge range of transformational possibilities and opportunities that can be leveraged at future points in time. So, in this slide, we will provide an example of a digital twin as illustrated in the diagram. The diagram, at first glance, may seem quite complicated, so we will break it down bit by bit. The use case is based upon a boutique risk and compliance consulting organization, which we will call ABC Corp. ABC Corp provides a variety of consulting services engagements around risk and compliance management in the finance sector. This is their primary value stream. This area is constantly evolving with new regulatory and compliance mandates being released by the regulatory bodies on a regular basis. With the advent of AI, and in particular the risks around managing AI systems, risk and compliance governance is now more complicated than ever before. To deal with these additional levels of complexity, ABC Corp are using digital twins to manage transformation around their primary value stream. They do this by breaking the value stream into a set of key systems so that they have a much more structured and granular view of the value stream. For each key system, they have a counterpart digital twin which models all components in the system, their relationships with each other, and how the system interfaces and interacts with other systems. As you can see in the slide, we have 3 digital twins. Digital Twin 1 will be the focus of our attention in this example. The objective of Digital Twin 1 is to model a critical in-house application that is being used to drive and support many of the external consulting engagements with clients. If the application breaks, this has a major impact on all consulting engagements. For Digital Twin 1, we are applying 4 separate contexts. Context 1, application component, risk metadata labels. Under this context, we are interested in any part of the application footprint that may exhibit some type of risk, for example, missing security patches, known vulnerabilities, not following application deployment best practices, and so on. If any entity, i.e. component in the system, exhibits any of these types of risk, we label or tag the entity with the corresponding metadata tag. We can also tag risk types to the relationships that connect entities together both inside or outside the system. By using tags, we can create any taxonomy we wish. For example, we could have a taxonomy that tracks all application components which are vulnerable to a specific software vulnerability. In our example, this metadata is being fed into a separate risk engine managed by the security operations teams. Because any type of metadata which is highly accurate can be fed into the risk engine, the security operations teams can execute very accurate risk assessments. Context 2. Application component security enforcement point metadata labels. Under this context, we are interested what security enforcement points such as firewalls, application microsegmentation solutions and so on are in path of the application footprint. We need to understand this for intra-application communications, i.e. communication between components of the application itself, and inter-application communication, i.e. when the application is communicating with other applications, users, back-end systems, and so forth. When you have a fully locked-down application to control security threats such as excessive lateral movement, which in turn provides protection from threats such as malware, any change to an application, by default, will break that application. Therefore, security policy changes need to be aligned and in sync with any changes made to the application itself. In small organizations, such as a boutique consulting firm, this is not so much of a problem. But for large organizations, such as global enterprises, this is a massive problem and one of the biggest security headaches that has to be dealt with. As organizations move towards a zero-trust global architecture in which you are not allowed to do anything unless explicitly authorized, it becomes even more painful. As before, we can tag entities with any type of metadata that we want. For example, does an application component, i.e. the entity, have local security enforcement technology deployed, such as application microsegmentation? Is there an upstream FW nearby to the application component? If so, then if we change something about that application component, we will probably need to change the corresponding FW security policy to ensure that we stay in sync. Context 3. Application component network path metadata labels. Under this context, we are interested in the network path information. For example, where is the application deployed? Is it deployed in ABC Corp's data center, or is it deployed in the cloud? The answer to that question will then affect what type of security is deployed. What happens if there is an application failure and disaster recovery needs to be invoked? Will the backup application be running in a different location, and if so, do the appropriate security enforcement points have the correct security policy running? I've witnessed many instances in which an application failed, DR was invoked, only for the backup application to fail because of broken connectivity, as the associated FWs had out-of-date security policies. Context 4 is very different from the others because it's not an infrastructure-related context. Instead, the context is all about tracking and managing regulatory compliance through multiple lenses. For example, the first lens refers to whether the application supports specific regulatory requirements, a common example being GDPR compliance. The second lens refers to which regulatory business processes the application is providing support for. For example, the application might be used by consultants to execute automated regulatory compliance reporting on behalf of ABC Corp's clients. Thus far for Digital Twin 1, we have discussed 4 example contexts. In fact, you can have any number of contexts, and you can design the metadata architecture to track any type of data points that you wish. This is the power of digital twins. With the right supporting architecture in place, they are incredibly flexible. The key to making this all work is using an event-driven architecture, or EDA, so that the digital twins can be updated in real time. Having point-in-time snapshots of system is not a workable solution because the models contained in the digital twin get out of date very quickly. We will discuss EDA in a bit more detail later, but for now, EDA is all about driving streams of data by pulling in relevant event information, processing that data, and then using it as a trigger to execute some type of function or process.
One thing is for certain in an organization, and that is that change never stops. A system that has recently been transformed will start to degrade over time. As the system ages, the value that it provides will also begin to degrade. To make matters worse, the larger and more complex the system, the faster the system will degrade if nothing changes in the system. As discussed extensively on the topic of theory of constraints, we first need to agree upon the goal of the system. The goal of the system determines what critical success factors and necessary conditions must be in place to ensure that the goal is reached. When we know what the goal of the system is, we can then start to define what the current state is. We can define this using a logical thinking tool called the current reality tree, as you may recall. We can also map out what the future state should look like using tools such as the future reality tree, and how to transition from current state to future state using transition trees, and so on. All of this takes a lot of effort. We do not want to see all of this effort go to waste and only live as knowledge in people's heads apart from a few logic tree diagrams. Most, if not all, of the current reality information should be codified into the digital twin model of that system. Doing so allows us to do the following. Number 1, see how the system is composed in terms of individual components or entities, and how these components relate to each other, i.e., what are the connecting relationships in place. Number 2, where the critical success factors and necessary conditions interface with the model and operate as dependencies. For example, a critical success factor might be that an application, which is vital to the execution of a business process in the system, becomes more resilient. Likewise, there may be a number of necessary conditions relating to the infrastructure that need to be in place to ensure that this critical success factor is met. These critical success factors and necessary conditions should be mapped as dependencies across the components in the digital twin model. Done correctly, it should be easy to see end-to-end causality, i.e., if the application fails, this is the chain reaction, these are the dominoes that will fall down, and the order in which they will fall. Creating digital twins of systems and processes that have been transformed provides the following benefits. You have a real-time model of the process/system itself.
In a real-time, always connected world in which customers expect products and services to be relevant, up-to-date, and providing continuous value through evolution, this does not bode well for static systems that are the bedrock of a supplier. Systems, whether they are comprised of one or multiple processes, must change, and ideally change to a better variation of what was in place previously. Consequently, a digital twin must represent a real-time model of the system in question. Digital twins can be updated in real time to reflect changes so that the model always accurately represents the actual reality. This means that digital twins must be event-driven in nature so that external events in other systems, which in turn affect the local system in question, can be captured with the appropriate context. As an example, if we have a critical financial application that we have modeled as a digital twin, and we find that a number of security vulnerabilities have been discovered for this application, this discovery event can be used to drive a number of actions. For example, we could append relevant security metadata so that we tag the parts of our digital twin, that is, our critical financial application, with this security vulnerability information. We are now able to visualize which parts of the application have which vulnerabilities. In addition, depending upon the level of modeling done, we would also be able to see which dependent business processes could be negatively affected if the security vulnerability in the application was exploited. Provides a point of reference for which parts of the system require future updates/transformation as part of a future iteration. When transforming a system, it's very rare that you will completely transform everything in its entirety. There is always more transformation work to be done. Even if the system is completely transformed, over time it will start to degrade because everything else outside of the system changes in some shape or form. Having a point of reference means that you never have to start from scratch again. In addition, lessons learned can be programmed into the digital twin model itself. For example, if a particular part of the transformation change was painful, inefficient, etc., that this can be captured as metadata. Thus, when it comes to transforming other systems, especially in different parts of the organization, queries can be performed in previous transformation activities to see whether there are any similarities to what is being planned now, and whether any lessons learned can be extrapolated ahead of time. This helps to ensure that history does not repeat itself. People move on with their careers. Even if no one is around from the original transformation, you have a tangible point of reference through the digital twin. How many times have you come to look at a system and found that there is no documentation in place? Even worse, the people who designed the system have all moved on. When you have a digital twin in place, this is not a big problem. Digital twins of systems can be aggregated into broader constructs, such as a value stream, so that stakeholders can view the value being created to the customer, which can play a significant role in helping to shape what true north is. A value stream, which comes from the world of lean-based system improvement, is the complete set of steps, including people, processes, and systems, required to design, produce, and deliver a product, service, or experience to an external or internal customer. A value stream encompasses every interaction from the initial customer request to the final realization of value, and its purpose is to identify and eliminate non-value-adding steps to improve efficiency, quality, and customer satisfaction. In the world of manufacturing from which lean originates, it is much easier to define what a value stream is and how it is constructed, because a physical product is being produced time and again. In the context of a complex service, a value stream may be much harder to define and subject to a lot of change, because components that comprise the value stream are changing all the time. In complex environments with complex value streams that are subject to a high degree of variation, manually defining and documenting a value stream becomes almost impossible because it is out of date almost immediately. When creating digital twins of systems that comprise a value stream using an event-driven architecture, it becomes possible to integrate these digital twins into a complete ecosystem that represents the complete end-to-end value stream. This is very useful because now it becomes possible in real time to see through the lens of the digital twin model an actual representation of the value stream that can be queried, interacted with, and dissected. For example, rather than guessing, it becomes programmatically possible to see all of the constraints, issues, and sub-optimizations that are inhibiting the flow of value through the value stream. We now have a powerful point of strategic reference because it now becomes much easier to see what true north is when it comes to transformation of the organization as a whole. For example, this can help to answer questions such as, should the organization retain its existing business model as it is and just focus on improving the existing value streams, or should it instead pivot to a new business operating model and create new value streams from scratch? Making the correct decisions can mean the difference between the organization being successful or the organization eventually dying.
In this section of the presentation, we will discuss some high-level approaches that can be taken around creating a digital twin platform architecture.
So let's take a moment to describe some of the features and capabilities of the building blocks that could comprise a digital twin platform architecture. Please note that this is an example architectural approach. There are many different ways of achieving the same outcome, so please take this information as you see fit and change it to meet your needs. The first important point to call out is that in this architecture, we have 5 or 6 key technology building blocks, which can be thought of as Swiss Army knives. They are off-the-shelf technology solutions such as graph databases, agentic automation platforms, data streaming platforms, etc. For each Swiss Army knife, we pull out the relevant blade or capability depending upon the use case at hand. What we ideally want are best-of-breed solutions for each of the Swiss Army knives so that we have the greatest level of flexibility around the blades that we can pull out and use. This is important because there are so many moving parts to a comprehensive digital twin platform that it is almost impossible to know exactly everything we will need up front at the start. There is an old saying, it's better to have it and not need it than to need it and not have it. For example, in the case of automation, we want a highly comprehensive automation platform which enables us to keep the number of automation solutions down to a minimum, which therefore simplifies the solution overall and hopefully reduces cost. Each Swiss Army knife can potentially be augmented with AI-driven capabilities. A good example here is agentic automation, which is particularly useful when automating processes which have a lot of variation in them. All of the technology building blocks are highly visual in nature. They each have their own GUIs and workflow engines, making it much easier for cross-domain teams to work on different components of the solution. It also makes it much easier to onboard additional resources when looking to accelerate the time for value later in the lifecycle of the platform. A key objective is to try move away from developer lock-in, in which only the development team can update a technology solution component. When we have a modular, decoupled architecture, this makes it much easier to migrate to new technology solution components when existing components no longer serve a purpose, by simply unplugging legacy components and inserting new ones in their place. We use an event-driven architecture, or EDA, which we'll discuss in more detail in a moment, to ensure that the system is able to deal with a vast range of change whilst offering the highest levels of performance, scale, and modularity. Lastly, because the digital twin platform is a foundational platform, it can be used for multiple purposes. So, as an example, it could be used as a pillar within a broader strategic zero-trust technology architecture. Note, we will create a separate set of video presentations around how the digital twin platform could be used to support strategic zero-trust initiatives within a large-scale organization.
In this slide, we will briefly describe each individual Swiss Army knife technology building block that makes up the digital twin platform. Rapid Application Development Platform, RAD for short, have become very prevalent over the last few years, particularly since they've started to integrate generative AI capabilities. RAD platforms, as the name would suggest, are all about creating applications to drive and support business processes and functions, but at a much faster rate of deployment into production.
As the world continues to speed up, businesses are under ever-increasing pressure to transform so that they can continue to compete. This results in the need to create new applications and to update existing applications at a much faster pace. RAD platforms are very useful when you need to create front-end systems or to create automation for elements of business logic which cannot be achieved through other systems such as IT process automation platforms. Of course, you don't have to use RAD platforms. You can develop your application or platform using traditional approaches, but it's much slower. There's also now vibe coding, using generative AI to create code, and that is certainly going to transform, and it is transforming, the software development industry. But it does require expertise to ensure that the AI-generated code works exactly as expected, and that it is production ready. There was no right or wrong answer here. However, the key outcome is accelerated time to value, but with safety. It's no good when creating a digital twin platform, having to wait many years for a basic set of capabilities to be made available. Services, Orchestration and Automation Platform, or SOAP for short. This is a phrase coined by Gartner and refers to class-leading enterprise-grade IT and business process automation platforms that can automate IT infrastructure, IT processes, work with legacy automations such as scripts, drive complex data pipelines, support application release automation, and many other automation use cases. These tools tend to automate all of the IT and business processes that happen behind the scenes, which users are oblivious to. They are the Uber orchestration/automation platform that operates quietly behind the scenes. A good SOAP platform can have literally hundreds of blades from which to choose from, and could be used for a vast range of automation purposes. A typical example of a blade that you would probably use would be to extract data from a legacy system, transform the data in some way, and then inject that data into another system for further processing. Data Streaming Platform, the DSP. This is the heart of the digital twin platform because it is the communications hub into which all technology components such as our Swiss Army knives plug into. Using the analogy of a car, this can be thought of as a high-speed motorway system. The primary responsibility of the DSP is to pull in streams of event information from other systems to store, potentially transform, and then forward these event streams to other interested parties. It is the technology component that makes an event-driven architecture possible. Integration Platform as a Service, iPaaS. The iPaaS platform is used to integrate applications, data, or other services components and to drive data pipelines through these integrations. Often there is some form of data transformation, for example, cleaning up legacy data which has quality and data hygiene issues, missing data that needs to be combined with other data sources, and so forth. Most iPaaS platforms have very good automation capabilities connecting systems together and transforming data that passes through these systems. Graph Database Platform. This is one of the most important technology components of the digital twin platform because it's in the graph database platform where we model systems as digital twins. It's very important to have the right graph database architecture in place in terms of scale and performance, particularly for large organizations which may wish to model a large range of highly complex digital twins. Such an approach can result in very large volumes of data and very high processing requirements. Another important capability is the ability to tag our digital twin with any type of metadata that we wish. The greater the flexibility, the greater than the number of use cases that we can support through digital twins. Lastly, another important capability is the ability to query the digital twins modeled in the graph database platform for any type of design information and to extract data in any desired format so that we can inject that information into higher level or upstream graph databases. A good example here would be if we were combining multiple digital twins together to create a digital twin representation of an organization's value stream, as we discussed previously. Agentic Process Automation, APA.
APA is a very broad technology area comprising multiple open source and commercial vendors. In terms of commercial vendors, many APA tools are evolutions of robotics, process automation, or RPA. So typically, this type of automation is used for user-facing business process automation. APA is incredibly powerful. APA can leverage AI to drive automation in business or IT processes, which may have a lot of variation. Traditionally, processes that have a lot of variation have not been good candidates for classic automation and orchestration tools because they're just too hard to automate and it's not worth the effort. APA changes all of this. In addition, APA tools offer the potential to provide very capable governance solutions for AI initiatives. As AI begins to integrate into ever deeper levels within the organization, it's critical to always take a safety-first approach, but to be able to do this ideally at real-time speeds. An AI tool that goes rogue can have devastating consequences for the organization.
In this slide, I want to dig a little bit deeper into stream-based event-driven architectures because it's such an important technology component. So looking at the left of the side, we can see a manufacturing bottling line in a Coca-Cola factory. As you can see, we have a conveyor belt filled with Coca-Cola bottles, or a stream of Coca-Cola bottles which are being processed by the factory's systems. In the Coca-Cola factory, the production system doesn't make a single bottle of Coke at a time. That would be incredibly inefficient. Instead, the process is broken down into a series of steps, and in each step we have a stream of activity. For example, in one step we will have a stream of Coca-Cola bottles being filled with product. In another separate step, we will have a stream of labels being stuck onto the bottles of Coke. Evolving this analogy and looking at the right-hand side of the slide, we have a digital twin that has been created which is being used to model a critical business application. This model is stored in our graph database. But applications always change. Perhaps the application has been transformed and migrated to the cloud. Perhaps the application has been integrated with another application, so who and what it communicates with is different. Perhaps part of the application has been updated to provide new capabilities so that it can drive changes to the business process. Regardless of the change, we need to be able to track that change in real time and ingest those changes so that our digital twin of the critical business application is always up to date. So how do we do this? Answer: we use an event-driven architecture. As you can see in the diagram, we have a function which is pulling in any application component infrastructure changes, and we are pulling in these changes as an event stream from an external system, such as the system which is hosting the application. We could also do some processing on that event stream to extract the information that we are particularly interested in, perhaps do some additional data transformation, and then use that as a point of reference to automatically update our model or digital twin which we have in the graph database. The key callout is that this is a real-time system. Updates are pulled in and processed in real time. It runs 24/7 and it never stops. Unlike our Coca-Cola factory, in which the production lines are fixed, we have unlimited flexibility around which data event streams we pull in, how we transform the data, how we filter the data. We can easily plug in automation tools to drive specific workflows. We can easily plug in code functions to drive sets of business logic and so on. So, in theory, if everything is architected correctly, you should always have up-to-date, real-time models of your digital twins. Having such a capability solves so many organizational IT problems because the decisions you take, whether they are made by a human or automated in some technology solution, can only be as good as the source data on which the decision must be based.
So now that we covered some of the basics on what a digital twin is and the platform we might construct to run and manage digital twins, let's spend a bit of time comparing two potential architectural patterns. Pattern 1. In-house developed technology stack. This pattern is based upon using a traditional monolith technology solution approach to create the digital twin platform.
All functions are hand-coded within the platform technology stack, giving complete control over every single line of code that is developed. The solution is created by a pool of developers who take complete responsibility for the development of the solution. If a feature is needed, this is made as a request, and the development team added to their backlog. Agile is used as the methodology to create, test, and deliver the capability requested. The general recommendation is that unless you have no choice, do not take this path, because there are a lot of moving parts to creating a digital twin platform architecture. This translates into a lot of development resources to create a comprehensive solution, and this takes a lot of time. The pros for Pattern 1 can be summarized as follows. There is complete control over the internal latency for communication between software components, as it's a single monolithic technology stack. Commercial license costs are reduced because off-the-shelf commercial components are limited as much as possible, because this pattern very much takes a build-it-yourself approach. Lastly, it reduces the reliance on external teams because all of the work is done by the same development team. The cons for Pattern 1 can be summarized as follows. The time to value is very slow, particularly if a traditional high-code development approach is used. You have to accept that there is a developer ring fence in place. It becomes very difficult, if not impossible, to go faster without additional developer resources. You really need to start with the end in mind because a re-architecture midway could prove very problematic. The last thing you want is to organically build the solution code as you go along without a clear direction of travel. This is because, particularly when combined with Agile, this can potentially result in a lot of spaghetti code, which is a nightmare to maintain and manage. Automation is either hard-coded into functions that have been hand-coded or called through external scripts. Whilst this is a cost-effective automation solution, it introduces a lot of problems when it comes to automation workflow reusability, extensibility, scalability, and supportability. Pattern 2. A distributed loosely coupled architecture. Pattern 2 takes a very different approach and is based upon creating a distributed loosely coupled platform using an event-driven architecture. The platform uses 5-6 Swiss Army knife systems which are highly extensible across technology components such as data streaming, graph databases, and agentic process automation, etc. A primary guiding principle is to ensure that the blades used from a Swiss Army knife are loosely coupled. This gives is a Lego building block architecture which makes it much easier to plug in new components or unplug end-of-life or legacy components. We look to visualize everything we can, including using a workflow-based solution, particularly for use cases such as automation. Hand-coding a function is kept to a minimum and is strictly controlled. With a distributed architecture, it's important to ensure that a constraint in the system, such as a slowdown or break in communications, does not cause the entire platform to grind to a halt. To ensure that is never a problem, all form of communication within the digital twin platform system and external systems are asynchronous in nature. Rapid application development, or RAD platforms, are used to create functions that drive business logic which cannot be offloaded to automation solutions. The general recommendation is that if you have the commercial budgets available, you take this path as it provides a much faster time to value with the ability to support significant change to the platform as it evolves over time. In addition, using this pattern, it makes it much easier to create a digital twin of the digital twin platform itself, that is, to drink your own champagne. Taking this approach makes the development of the digital twin platform much more structured and surgical over time, resulting a simpler overall architecture but with a higher level of capability and without any critical security gaps. The pros for Pattern 2 can be summarized as follows. You don't have to have a complete vision of the target end state. Because of the modular nature using loosely coupled architectural design principles, there is a strong ability to change architectural direction if needed based upon experimental learning and experience over time. Asynchronous communication ensures that you don't get any bottlenecks, which could grind the system to a halt. The cons for Pattern 2 can be summarized as follows. Swiss Army knife platforms such as enterprise-grade IT process automation and agentic process automation that have lots of blades are often expensive commercial platforms. Note that not all Swiss Army knives have to be commercial platforms, however. A hybrid approach can be taken in which open-source software may be used.
However, in the event that the digital twin platform becomes highly strategic to the organization, the use of open source software should be used with care. And depending upon the size of the organization, you may need to get support and buy-in from multiple teams across the organization. A common challenge is that each Swiss Army knife might be under different ownership.
Well, that's the end of the presentation. We hope you found it of value. We'll finish off with a few closing thoughts. Combining together a world-class thinking framework along with a high-quality digital twin technology platform is a powerful combination for any organization. They complement each other, but they are not dependent on each other. All people within an organization are capable of world-class thinking. Background, age, experience, education, IQ, all of these things are irrelevant. To unlock world-class thinking in people, 3 things need to happen. 1, there needs to be spare mental capacity in the person. GTD fixes this. 2, we need to move away from letting our egos call the shots. Instead, we need to take a step back to appreciate the systems around us and learn how to recognize the real problems in these systems and to create sustainable solutions. The theory of constraints and its logical thinking processes gives us this. 3, we need to unlock the innate wisdom that is in all of us and which comes as part of the human OS. Time to think creates the optimal thinking environment in which our best thinking can step forward.